Okay, so today we're going to actually get into what is probability properly. So last time we did kind of just a real basic review of set theory, kind of set notation, even more basically. Now we're going to talk about what probability is from kind of a mathematical standpoint. So we all have lots of intuitions kind of when we talk about the likelihood, the probability of something happening. And in this course, we're going to axiomatize. That is, we're going to set down a set of rules about mathematically what does it mean to talk about probability. And so this we're going to refer to as axiomatic probability, and that's the lecture title for our second lecture, lecture 2. So we're going to spend the first part of this lecture defining a bunch of terms, kind of getting the vocabulary of probability straightened out. And then we're going to talk about what it means to be a probability, or what we're going to call a probability function. And we're going to kind of develop, or start to develop this lecture, some simple examples of probability functions. And the next lecture, we're going to go take those kind of simple examples and expand them, talk about basic theorems that we know about all probability functions. So in this lecture, we're going to start off by defining the kind of most simple, basic item in probability theory, and that is the sample space. So our definition of a sample space. And the sample space, typically in this class we're going to note as a capital script S. And this is going to be the set of possible outcomes. So the sample space is the set of possible, let's write that correctly, possible outcomes. So what we're imagining here is that we do an experiment, a random experiment, and we don't know, being that the experiment is random, what the outcome of the experiment is going to be. But we have some sense of what the possibilities are. And so that set of possibilities is what we call the sample space. So I'm going to denote that with a capital S. And let's look at some examples. So an example, my random experiment might be I flip a coin once. So I flip a coin. And so this kind of experiment of flipping a coin has some possible outcomes. Well, what are my possible outcomes? I could either get a heads or I could get tails. And so my sample space, capital S in this case, is H or T. H for heads, T for tails. So another example, maybe I roll a 6-sided die. And I'm going to observe the number, I believe it's called the number of pips on the side of the die after I roll it. What are the possibility for the number I could get after rolling it? Well, I can get 1, 2, 3, 4, 5, or 6 different pips. So my sample space is 1, 2, 3, 4, 5, or 6. Now, it's possible, say if I go back to my first example, maybe my coin could land on its side. If I flip a coin, maybe it doesn't have to be heads or tails. It could come up heads, could come up tails, or it could kind of land exactly on its edge. And ultimately, the decision of what the sample space is going to come down to a modeling decision. So maybe I roll a 6-sided die and it falls off the table into the trash and I never recover it. Is that an outcome? Well, how am I modeling the phenomenon? So I'm an applied statistician, and so I think about these as kind of we're using mathematics to model the world. So in some ways there is no capital T truth to what the correct way to model it is, or at least you'd have to talk to the physicist about that. But in our world, we're going to talk about reasonable ways of modeling sample spaces. And so if I flip a coin, a reasonable way of modeling the possible outcomes is heads or tails. And if I roll a 6-sided die, the reasonable way to kind of model The roll of 6-sided die is, okay, it can come up any number 1 to 6. Some other examples. I could roll 2 dice, 2 6-sided dice. In that case, I could get, say, a 1 on the first die, a 1 on the second, a 1 on the first, a 2 on the second, a 1 on the first, a 3 on the second, a 4 on the first, 6 on the second, right? And so in this case, so I'm going to observe kind of ordered pairs. I could get 1 on the first, 1 on the second, 1 on the first, 2 on the second, 1 on the first, 3 on the second, and so forth. I could get 2 on the first, 1 on the second, 2 on the first, 2 on the second, and so forth. So you can imagine there are a bunch of possible outcomes, and ultimately what this set is it's a set of ordered pairs, I, J, where I and J are between 1 and 6. So here I've written the ordered pair IJ where 1 less than or equal to I and J less than or equal to 6. So this is kind of my notation to say I and J don't necessarily have an ordering, but they both are bounded between 1 and 6. So here are some examples of discrete sample spaces where the outcome of my experiment can take on one of a finite number or discrete number of outcomes. But I can also have what we call kind of continuous, or an outcome from the experiment can kind of range in some continuum of values. So for example, if my experiment might be waiting for a bus to arrive, and so I can say my outcome might be, my sample space might contain the amount of time you have to wait for the bus to arrive. And again, there are different ways of modeling this problem. You could model it down to a discrete number of milliseconds, but typically for something like time, we're going to model it as continuous, as taking on values to some continuum, some compact set, some set of the real line. And so maybe in this example, I say my sample space is any number between 0 and it's unbounded, 0 and infinity. It could arrive anytime between now and any finite time in the future. And so my way of modeling that might be to say, well, my sample space is the half open or half closed set 0 to infinity. And that seems like a reasonable way of modeling that probabilistic phenomenon. Of course, we'd have, so this example of waiting for a bus to arrive is, now I have an infinite number of outcomes possible in my sample space. And the values we kind of say very loosely, don't ask any of the pure math professors to verify this, but we say it ranges in a continuum. So typically that means some set of the real line, or some higher dimensional space. So that is an infinite number of outcomes, but we could also have a discrete outcomes, but also infinite. For example, maybe my experiment is to look at the number of customers arriving in my restaurant. And they're going to record how many customers arrive in my restaurant. So you can pause and you can think, okay, what's a reasonable way of modeling the number of customers who might arrive in my restaurant? I'm going to argue that one way of modeling the sample space is what I'm going to call the natural numbers indexed at 0, or starting at 0. So that is the kind of counting numbers and 0. So 0, I could have 0 customers arrive, I could have 1 customer arrive, I could have 2 customers arrive, 3 customers arrive, 4 customers arrive. I could have any number of finite number of customers arrive, but I can't have 1.5. I can't have half a customer. So there's still what we're going to call is discrete, because I kind of have a quanta in the number of customers arrived. It's either 0 or 1. It can't be anywhere in between. But there's still an infinite number. So to summarize, so this again has an infinite number, but they're kind of discrete. There are a couple different types of sample spaces in summary. So let's just write types of sample spaces. And the simplest type of sample space is a finite sample space. And finite sample space would mean if we look at the cardinality of S, that it is less than infinity. So those are any of the first examples I looked at where I have a finite number of outcomes. And of course, the other kind of major type, is infinite or infinite number. And I'm going to be very kind of loose here with notation. Just say there is an infinite number of outcomes in my sample space. More specifically, this we know from let's say 214. We know there are two types of infinite sets. The first being we could have a countable number of outcomes in my sample space. So for example, I could set my example number of customers arriving at the restaurant n sub 0 is countable. It's in a one-to-one relationship with the natural numbers. And the second type of infinite sample space is, of course, uncountable. And that would be, for example, waiting time for the bus. I was going to model as the half closed interval 0 to infinity. That does not have a countable number of outcomes. And this is going to matter as we go through the course. So these are just good things to keep in mind. And this is why a class like 214 is a prereq for this, because you need to be comfortable with these kind of concepts. Okay, so sample spaces. It's a pretty simple idea. It's basically a modeling choice, but it is, we're just going to enumerate what's the universe of possible outcomes from my random experiment. And I've used this word outcome several times, so let's formally define what an outcome is. So let's say definition, outcome. And outcome is just the probabilist way of redefining what an element of the sample space is. So we call elements, let's say some little s in my capital S sample space. Oops, let's write this a little more legibly. So elements of my sample space, little s, we call these elements, quote, outcomes from my experiment. So capital S here is my sample space, and little s here is my outcome. So the sample space is the collection of all possible outcomes. And so that's kind of natural notation there, or natural terminology. So example, again, if I take my example where it's rolling a six-sided die, so my sample space, my set of possible outcomes was 1, 2, 3, 4, 5, 6. Then 1 is an element of my sample space, and therefore, so 1, as it were, getting a 1 on my die is an outcome. It's a possibility of what I could get when I roll my die. Okay. So sample space, we have outcomes, and if we have a collection of outcomes that's not the whole sample space, we're going to call that an event. So a super important definition is that of an event. So very simply, an event is renaming a subset of the sample space. So probabilists like to be confusing. We rename the whole set of universe possibilities sample space. We rename elements outcomes, and we rename subsets of the sample space events. So an event, E, typically, is a subset of the sample space. Sample space, typically denoted capital S. I.e., well, let's just write events or subsets, or let's just use the simple subset of the sample space. So there you go. Very simple definition. We're just renaming some things you already know. So subset is a specific type of set. And when you're talking specifically about subsets of the sample space, we tend to call them events. So let's look at some examples. Examples is that, so my experiment was I roll a die, right? And my outcome, or my sample space, was my set of possible outcomes. My outcomes could be 1, 2, 3, 4, 5, or 6. And so if I look at E, which is going to be the set containing numbers 1 and 2, this is a subset of the sample space, surely, because 1 and 2 are elements of S. And so it's a particular event. What is the event? Well, E basically represents the event of rolling a 1 or a 2. So I could look at different collections of outcomes. We call those events. So for example, the event of I roll a 1 or I roll a 2 would just be the subset 1, 2. That's an event. That's what we call it. And we kind of have this terminology where we say an event happens or an event occurs if the kind of quote observed outcome of our experiment is an element of E. So this is all a bit, this is not particularly mathematically precise, but terminologically what we say is that an event quote happens if the observed outcome of the experiment is an element of E. So we have this kind of understanding of what's going on where we have some experiment we're going to do, has a non-deterministic outcome, has a random outcome. We have a set of possible outcomes called the sample space. And we could say an event occurs, and we kind of then do the experiment. And if, say, 1 is the number that comes up when we roll the die, we'd say this event E occurs. Alternatively, if we roll 2, we'd say E also occurs. Okay. So some other kind of events. Let's look at another example. Here's a question. The sample space. Is the sample space an event? You can pause and you can think about it for a second. So the sample space is definitely an event because the sample space is a subset of the sample space, right? Every set is a subset of itself. Events are just renaming subsets of the sample space. Since S is a subset of the sample space, we can say hence S is an event. What event is S? So if we go back to our dice rolling example, the event E was rolling a 1 or a 2. What's the event S, which is the set 1, 2, 3, 4, 5, 6? So you can pause and think for a second. Well, S is going to basically be the event that something happens or occurs when we do the experiment. So you could think, and we'll get to this formally, definitely by next lecture, something probably should happen. If we defined our sample space well, then our intuition is that something should happen. So you can think about what the probability of, and eventually we can start talking about probability of these events, what the probability of S occurring is. So you can think about, okay, S is the event that something occurs, is something that any of the outcomes happen. Probably that has to happen, right? So you can think about what you think the probability of something happening is. Another example is if I look at the null set. Is the null set an event? So you can pause and think here. And of course, the answer is it is. Why? Well, the null set is the subset of the sample space. The empty set is a subset of every set. So the empty set is an event. So if S is the event that something happens, what is the empty event signify? And I don't think I have a good answer for you on that one. So the empty event is kind of a mathematically convenient thing to have. You could say it's the event that nothing occurs. It's a reasonable interpretation. It's a little bit hard to interpret, but it is indeed an event. It's a very important event. So in some ways, it's the event that nothing happens, maybe. Let's say question mark, nothing happens. It's a bit hard to interpret, but it's a super important event, and it is definitely an event. And we're going to talk next lecture about what the probability is that, say, nothing happens. Okay. So those are the basic definitions. So we had sample space. Sample space is the set of possible outcomes. An element of the sample space we called an outcome. And subsets of the sample space we called events. And what we really want to do is we want to talk about the probability of certain events happening. And so this leads us to the main point of the lecture, which is axiomatic probability. That is, we're going to build up a set of axioms or rules about how we are allowed to assign probability to events. Turns out, you can't do whatever you like. And there are certain rules kind of that follow from basic intuition about how we think probability behaves. Broadly, what we want to do is that given an experiment, some random experiment that is a sample space S. So we have some experiment that has a bunch of possible outcomes. We don't know beforehand what's going to happen, but we have a sense of what the possibilities are, and we codify that mathematically as the sample space. And what we want, so that's what we're given, what we want to do is for any event, so that is some E that's a subset of my sample space, we want to assign some, let's call it measure, of the likelihood that my event happens or occurs. So we're given an experiment, codify that as a sample space, and what we want to do in the probability class, and we're going to develop how to do this, is we want to build a set of rules and kind of explore those set of rules about how are we allowed to build up a measure for each set. We want to kind of have a measure and say, well, this event is likely, this event is not likely, this event's more likely than that event, this event will happen, this event won't happen, this event, etc. So what we want to do is determine some measure of the likelihood that each event occurs, that each subset of my sample space occurs. And of course, we call this measure of the likelihood a probability. And this word measure is quite loaded. If you take a graduate level probability class, it's just called measure theory. So mathematically, what we want to do, of course, this is a math class, so we want to, for each event, and that's a subset of my sample space, assign a probability. And of course, how do we do that? If I take something and I assign to each something number, we call that putting it in a function, right? So we want to assign a probability. I'm going to denote the probability of E happening as P of E. So this bold P, so this is the probability of E occurring. So for each element of my sample space, or sorry, for each subset of my sample space, that is each event, I want to assign a probability to that event. So for each E, that's a subset of my sample space, I'm going to assign a probability P of E. So we're effectively going to be building up a probability function. So this P is a probability function. It's a function that takes in subsets of the sample space and spits out the probability of that subset. As it takes in events and it spits out the probability of that event. And this lecture, we're going to discuss a valid way of defining a probability function P of E. We're going to have some choice depending on how you want to model the phenomena. You can build different P, but there are certain rules you have to adhere to. So we're going to discuss what are the rules for building a probability function, P. And when we build up this P, of course, we want this probability function P to be, one, mathematically consistent, right? Better be a valid function. There's certain rules about functions that make them valid. Think about 214. But as importantly, I'd say as an applied statistician, we want this probability function to be somehow to preserve or encode, let's say, some of our intuitions about probability. So we all kind of have an intuitive sense about what probability is and how it behaves and how we can do some math. We're not always right in our intuition, but we have some intuition about kind of what statements we can make. And so we're going to build up some rules that kind of preserve and encode some of that intuition, but we're going to do it in a mathematically consistent way. Okay. So let's not delay any further. Let's talk about what is a valid way of building up a probability function. So I'm not going to tell you exactly what probability function. Depends on the thing you're modeling, right? So sometimes you'll model certain events as being more likely than other events, and sometimes you'll model reverse. Depends on the phenomena you're modeling and what you're doing with the probability functions, kind of an applied way. But there are certain rules regardless of how you're going to assign probabilities to events. There are certain rules you have to satisfy. And so certain rules that make this probability function mathematically consistent. So this leads us to a super important definition, which is a probability function P. So why is this a definition? It's defining what is allowed for a, quote, valid probability function. So we're going to set down some axioms of a probability function. If my script P here is a probability function, it must satisfy these, and if I have a function that satisfies them, it is a probability function. Okay, so given a sample space S, a probability function is a function. Well, that's a good start. Probability functions better be functions. And it's a function P. Now, in order to define the function, of course, I have to tell you what is its domain and what is its kind of codomain or range, as you might say. So I'm going to say pause here, think about what is my probability function taking in. So usually we write something, and then we write an arrow, and then we write something else, right? So this should be the domain, and this should be what's often called the codomain or range. Codomain is probably a better word, right? So what is my probability function taking in, and what is, or from what set is it taking in, and what is it spitting out? So, of course, our probability function is taking in a set, a event E, right? So we scroll back up here. It's going to take in events E, and it's going to assign to them a measure P of E. That's how we denote functions, right? So it can take in any possible subset of the sample space. So the domain, the things that the function can take in, is any possible subset of the sample space. What's that called? It's called the power set. So our domain, I'm going to say, is P of S. It takes in events, E, that is elements of the power set, subsets of S. The power set is the subsets of S, so it takes in elements in the power set. It takes in subsets of S. And it spits out what? It's going to spit out a number, a numerical measure of the likelihood of an event happening, right? So we take in E, and we spit out a numerical measure, P of E, telling us how likely E is to occur. And so in this course, that is going to be a real number. So a probability function takes in a subset of the sample space, an event, and spits out a measurement, P of the event, that corresponds to how likely it is for that thing to happen. So it goes from the power set of the sample space to the real numbers. If you talk to physicists, they often work in complex numbers, and that's a whole another field that applied statisticians tend not to work in. But this is a good enough definition to be going on for this course. So is a probability function any function that takes in an event and spits out a number? Well, the answer is no, otherwise this would kind of be a very silly definition. The definition of a probability function is a function going from the power set of the sample space to the real numbers that satisfies, say, so given a sample space probability function, let's say probability function, let's say P is a function, P goes power set to real numbers, that satisfies what are called the Kolmogorov axioms. So that's a fancy way of saying the rules that this guy called Kolmogorov came up with in the 20s. These are a really good set of rules. So a probability is a function that takes in an event, subset of the sample space, spits out a number, but it's going to satisfy certain things. These things are called the Kolmogorov axioms. You will memorize them by the end of this course. And the first Kolmogorov axiom, there are 3 of them, is the axiom of non-negativity. Positive vibes only, right? So the axiom of non-negativity says that if I look at P of E, the probability of an event, so I take an event from my domain, I throw it in P, I get out a real number called P of E, right? That number better be non-negative. So the axiom of non-negativity says that the probability of any event is bigger than or equal to 0, and this is true for all events in my sample space. So that's what we'd say, or for all E subsets of S. So the non-negativity axiom encodes some intuition we have that probability shouldn't be negative. Now, if I started this course and I said probability can't be negative, everyone would nod and say, yes, yes, okay, we know that, right? It's intuition we have about what it means to be a probability. You can't have a negative likelihood of something happening. It doesn't make a lot of sense. And so Kolmogorov said, yeah, that's an intuition we want to preserve when we're going to mathematically codify, which is effectively what we're doing here, what a probability means mathematically. One of the things we need to codify is that, well, probabilities aren't negative. We don't really make much sense of those. So that's axiom 1, non-negativity. The second of the 3 Kolmogorov axioms is unit measure. And the unit measure axiom says that the probability of the sample space is 1. So let's back up, right? We said before the sample space is an event. The sample space is the subset of the sample space, subset of itself. Therefore, it's an event. Therefore, we're defining a function called P that can assign probabilities to events. So we should be able to assign the probability to the whole sample space. We said the sample space is basically the event that something happens. So the unit measure axiom says that the probability something happens is 1. That is, 100% of the time, something better happen. So when we talk about probabilities, kind of as an aside, we talk about, as we'll see, we don't tend to talk about them in percentages. So statisticians tend not to do that. We tend to talk about them as fractions. 1 kind of corresponds to 100% probability. And I'll go back and forth a little bit, in a relaxed manner between percentages and not, but we just tend to talk about it as a fraction. But the unit measure axiom says that another intuition we want to preserve is that the probability of S, so it's the probability of something happening, the probability of the event that something happens, should be 1. Something better happen. I do my experiment. If I've defined my sample space S correctly, something better happen. Otherwise, kind of I need to expand my sample space in some way because I'm not really capturing all the possible outcomes. So this is another kind of choice that we have, or that Kolmogorov had. Turns out this is a really good idea, and it codifies intuition. First intuition we codify is that things better be positive, that probabilities better be positive. The probability that something happens better be 100%. When we do the experiment, something better happen. And the third and final axiom is not as intuitive as the other two, but it's the axiom of countable additivity. So the axiom of countable additivity, right? Recall what we're doing. We're trying to give the rules of what it means to be a probability function P. A function that takes an event and assigns a likelihood score to it, called a probability. Better be non-negative. There's probability something happens better be 1. And the last axiom is the axiom of countable additivity. Countable additivity says that if I have a partition, E sub I, I'm going to be a little relaxed. Let's just say E sub I goes 1 to infinity. So this is if this collection of sets is a partition of my sample space, right? So why did I introduce partitions last time? Exactly this point. A partition means it's going to, so let's draw a picture here. So let me back up here. I actually don't need it to be a partition of the whole sample space. It's going to be a partition of some event E. Okay, so let's back up here. Here is my whole sample space. In my sample space, there is some event E. And I'm going to partition E into a set of smaller sets E sub I. So maybe E sub 1, E sub 2, E sub 3, E sub 4, E sub 5, and maybe E sub 6, right? Now, in theory, we could have a countable number of these. So you could do it, partition E into an infinite countably infinite number of sets E sub I. So the E sub i's partition, they basically shatter E into these non-overlapping sets, but if I union all these sets back, I get E, right? So to say the E sub i's partition E, what I mean is that E sub I intersect E sub j is empty, as long as I is not equal to j, and 2, if I union I goes 1 to infinity of the E sub I get back E. So if I look at this partition, and in particular, I consider this second point here, which is that I can reconstruct E by taking the union of the E sub I. The axiom of countable additivity says that if I want to take, let me write this in blue so it's the same color. If I want to look at the probability that E occurs, I don't actually have to know anything about E beyond this partition. And in fact, I can just sum up the probabilities of each of these events individually. So I'm going to put a period there. That is the whole axiom. If I partition an event E into some countable partition of E sub I, the probability of E can be calculated as just the sum of the probability of the E sub I. Now this could be an infinite sum. Luckily we've all taken Calc 2, we know how to deal with that. So if we look back at my picture, in red here I have E, and you can think of the probability of E as like the ratio of the area of E to the area of S. It's a totally reasonable way of thinking about probability. And if I wanted to get the total kind of area of E, what I could do is just sum up the area of the E sub I. So let's say area of E, this is a statement everyone will agree with, is equal to sum of the areas of the E sub I. And if probability can kind of broadly be interpreted just as kind of a percentage of E to the total area of S, then the probability of E can be gotten by summing up the probabilities of the E sub I. So it says we can do something really nice. Is that if we have a partition of an event, we can just sum up the probabilities of those partitions and get back the original event. So basically, it's got some kind of distributive law. So countable additivity gives us a distributive law where basically I can say, if I want to look at the probability of E, well, this is the probability. I can write E as the union, I goes 1 to infinity, of the E sub I. And what I'd like to do is kind of just distribute this P over. So what I'd like to do is kind of say, okay, this is the union, I goes 1 to infinity, probability of E sub I. But that doesn't make any sense. How do I take the union of these numbers? No, I got to change the union to a sum. And that's the law of countable additivity. I'm allowed to distribute P over a union, but I have to change the union to a sum, and I'm only allowed to do that if I'm taking the union of a partition. That is disjoint events. The events in my union better be disjoint. So it's basically a distributive law, let's say, for disjoint events. And we'll see later that you can do this kind of distributive thing where you distribute the probability measure over a union and change the union to a sum, but you can only do that if the things are, the events, the E sub i's, are disjoint. So that's the third axiom, and that ends our definition of a probability function. So let's just go back and recap what's going on here. We started off and we said we wanted to define what the valid rules are for a probability function. The probability function, as we said, is going to take in events, and it's going to spit out probability, a numeric measure of that event, probability of that event happening. So it's a function, it takes in elements of the power set of the sample space. As it takes in subsets of the sample space, we call the subsets of the sample space events, and it spits out a number, a numeric measure, called a probability. In order for this P to be a valid probability function, it better satisfy certain mathematical rules that codify our intuition about how probability works. The first being that probability better not be negative, non-negativity. The second being that the probability something happens better be 1. And the third being that I can basically do this area thing, where if I want to calculate the area, that is the probability of an event E, I could, and I break apart E into a set of disjoint sets, a partition, I can get back the probability of E, or the area of E, kind of equivalent things, by summing up the area, or the probability of the constituent little pieces. I can do that as long as these E's really do partition. These E sub I's really do partition E. That is, they don't overlap, and if I take the union, I get back the whole thing. So this is the axiom of countable additivity, and it's kind of a distributive law in some ways for probabilities. I can distribute probabilities over unions as long as things in the union are disjoint. We'll codify that as a theorem specifically probably next lecture. So that's the third one that codifies some kind of intuition about how area or measurements can be made of things. You can add together measurements of things. If I want to measure the size of something, I can split it in two, measure each of the two parts, and reassemble that. And probability is a measure. It's a measure of the likelihood. So I better satisfy that intuition. So if I have a function that satisfies those three laws, non-negativity, unit measure, and countable additivity, it's a probability measure. And vice versa, or vice versa. Any probability measure satisfies those. If I want to build a probability measure, it better satisfy those. Okay, so let's look at some examples. And let's start as simple as we can. So our simplest example, and you're going to get tired of this example, but our simplest example is that I'm going to flip a coin. So what's my sample space, right? Shouldn't be too bad. Sample space, I can either get a heads or I can get a tails. Possible outcomes: heads, tails. Sample space is HD. What's a valid probability function? A valid probability function on S. What's a probability function? A probability function is you can take in subsets of S and spit out a measure of the probability of the subsets. So, for example, my probability function will take in the subset H and it will spit out some number. It could take in other subsets, other events. So H is the event that I get heads. It's going to take in the set just containing T, that's the event that a tails happens, and it's going to spit out another number. And the probability, to define a probability function, I actually need to define this function P for all possible subsets of my sample space here. So what are the other possible subsets I would have to define this for? Well, H or T, what's the probability I get a heads or a tails? That's another event. Or what's the event? Of course, that's a subset of every set is the empty set. So that's also, I have to talk about what the probability of the empty set. So I have choice. And with an applied statistician, I'm going to build a more complicated model than this, but they'll build a model. And they're going to have choices about what are the values that they assign to the various events. But they don't have an infinite number of choices. or rather, they don't have unconstrained choices here. There are rules about what choices I'm allowed to make. So what's a really reasonable probability function? Well, the probability function we want to all say is that, okay, the probability of getting heads should be half, the probability of getting tails should be a half. Probability of getting heads, tails, that's the event S. That's the whole sample space. That's the probability that something happens is 1. You either get a heads or a tails. And the probability that nothing happens, that's the probability of the empty set, let's say it's 0. So I've told you this is the probability function, right? So a function just takes in subsets, spits out numbers, and that's a valid enumeration of the function, possible probability function on my sample space HT. Question I have is that a valid probability function? Does that satisfy my Kolmogorov axioms? Is this allowed? So let's check. We can check the Kolmogorov axioms. So let's check if this is a valid probability function. How? We need to check the axioms. What's the first axiom? If this is a valid probability function, a valid way of assigning probabilities to subsets of my sample space, valid way of assigning probabilities to events, it better satisfy my Kolmogorov axioms. The first is that of non-negativity. The probability of any event E is bigger than or equal to 0, and this is for any event. For any event E, that's a subset of my sample space. Is that true? By inspection, true. Half is bigger than 0, half is bigger than 0, 1 is bigger than 0, 0 is bigger than or equal to 0. Check. The probability function is non-negative. Okay? 2. My second axiom is that the probability of something happening better be 1. 100% of the time, something happens when I do my experiment. Is that true? Yeah, I've just said it's true. So this specific part of my definition ensures that that's true. So I very cleverly chose that because I knew I had to satisfy the axiom. Okay, so it has non-negativity, as a unit measure. And then the last one I have to check is I have to check countable additivity. So we're not going to, presumably you have to test this for all possible countable partitions of any possible event. So that's a tall order. But I'll show you one example, and I'll leave the rest for you to think about why it's true. So this would say is that what I need is that the probability of the union I goes 1 to infinity e sub I is sum 1 to infinity probability of e sub I for any partition e sub I of any event E. So that's a lot to check. Talk infinite number for any possible event. There are actually only a finite number of events. The 4 we enumerated up top, but there's potentially an infinite or countably infinite number of possible partitions. But there, you could think about how you can get it down to kind of a finite number of things you need to check, and you could make some arguments. Let's just look at it for one example. So let's E1 be the event I get a heads. So that's H. E2 be the event that I get a tails. That's T. What I want to check is that if I look at S, this is partitioned into E1 union E2. All right, E1 and E2 partition S. They're disjoint, and their union gives me back the whole sample space. And so it better be true that the probability of S is equal to the probability of E1 union E2. That's just true because there's set equality, but that better be equal to the probability of E1 plus the probability of E2. And that's going to be true in this case. The probability of S, we said before, is 1. The probability of E1, the probability of getting heads, is 1/2. And the probability of getting tails is also 1/2. 1/2 and 1/2 is 1. So we're good, at least in this example. That's actually the hardest part about the whole proof. But you can think about more generally how you'd argue for this. Okay. Are there other ways of defining this probability function? So I chose certain numbers. I chose a 1/2 here, I chose 1/2 here, I chose 0 here, I chose 1 there. But there's nothing that said in Kolmogorov axiom that said I had to choose those numbers for this particular sample space. Are there other valid choices that would give me valid probability functions that satisfy Kolmogorov's axioms? So what if I were to say probability of S is 1, probability of the empty event, nothing happening, is 0, the probability of the event of getting a heads is some number alpha, where alpha is between 0 and 1, and the probability of tails is 1 minus alpha. Is this a valid probability function? So I'm not going to do this. I'm going to tell you it is. I think your intuition is, yeah, this should be valid. And I'll let you think about, it's a good exercise, why. Can you check the Kolmogorov axioms for this? Non-negativity, unit measure, and countable additivity. It's going to be kind of similar to the previous one, but I've generalized it. It doesn't have to be 1/2. 1/2. It's basically a weighted coin, right? Where the weight of the probability of heads is alpha. And our intuition is this should be a valid way, another way of defining probability function. And so you see here what I'm talking about when you kind of doing an applied problem. I'm going to model, say, my experiment of flipping a coin. Now, it might be that the coin is fair, in which case I'm going to model it as 1/2. But it might be I know the coin is not fair, in which case I'm going to choose a different way of modeling it. Maybe I choose some weight alpha with the probability of heads, and correspondingly 1 minus alpha is the probability of tails. And so in this class, we're going to build up tools for how you can manipulate probabilities. And, in the applied class, say like 452, or any of the other applied courses we have, 352, etc., you can apply these modeling tools to probabilistically model phenomena, and that's the field of statistics. Okay. So we're going to close with a theorem here. And the theorem is basically going to prove the previous question, but it's going to prove it more generally. And the theorem is going to say that one of the common ways of building up a probability function is a valid way of building up a probability function. So let's look at an example. The example might be, I'm going to have a basket. So here's my drawing of a basket, and it's going to have 3 balls in it. Ball 1, ball 2, and then it's going to have a third ball, and that one's much bigger than the other 2. Now I could ask each of you, okay, define the probability of drawing each of the 3 balls. If I reach into the basket and I draw one, what's the probability I draw ball 1 or ball 2 or ball 3? And probably what you're going to do is you're going to pick out 3 numbers. So my sample space in this case, let's say, is 1, 2, 3, corresponding to balls 1, 2, or 3. And the way that if I would ask you to find probabilities, maybe I tell you that the probability of it's 2 times as likely to choose ball 3. How would you build up a probability function for this? If you know nothing about Kolmogorov axioms or anything, what would you do? You would pick 3 numbers. You would say, okay, corresponding to each element of my sample space, I'm going to pick a number P1 corresponding to 1, P2 corresponding to 2, and P3 corresponding to 3. And I'm going to make them probabilities. So what do they have to be? Well, they better not be negative. I'm going to make them sum to 1. So maybe I should choose 1/2, 1/4, and okay, 1/2 and 1/4, 3/4. So I better have kind of 1/4 left over. That's 1/4. Now that's kind of what anyone would do. But there's nothing in Kolmogorov that says you have to do it, but it's a totally reasonable way of doing it. And basically what it is that for each element of my sample space, I'm going to assign some number, p sub I, between 0 and 1. I'm going to assure that they sum to 1. The total probability across all the elements is not bigger than 1. Somehow we think that has to be true. It does, but we haven't proven that, actually. And if I want to, say, calculate the probability of a certain event, maybe I want to calculate the probability of choosing ball 1 or ball 2. So that's probability of the subset 1, 2. What would I do? I would say it's 1/4 plus 1/4. So I'm going to add together P1 plus P2. So to calculate the probability of any event, I'm just going to add the P sub I corresponding to the elements of the event. So if I wanted the probability of 1 or 3, oops, that's not super legible. Let's say of drawing ball 1 or ball 3, I'm going to say, okay, 1 is in my event, so I'm going to say P1, and then 3 is in my event, I'm going to say plus P3, so that's 1/4 plus 1/2 is 3/4. And this is a totally reasonable way of building up a probability function. The question is it a valid way? We define these Kolmogorov axioms that claim that they codify our intuition about probability. But we haven't actually shown that this kind of simple way of defining a probability function is valid according to Kolmogorov. Hopefully, if Kolmogorov's axioms are reasonable, this is going to be a reasonable way of building a probability function. And indeed it is. And so it's kind of our first major theorem. Not that major, but first kind of nice little theorem. Puts you to at ease that kind of simple ways of building up probability functions is valid. So theorem is called the finite sample space theorem. And what it says is that if I have a sample space that has a finite number of elements, S1, S2, S3, all the way up to some S sub n, finite number of elements, so that is the cardinality of my sample space is little n is less than infinity. And to build up a probability function on this, I choose corresponding to each of my S sub I, P1, P2, P3, P sub n, where 1, each of these P sub I is bigger than or equal to 0, and 2, if I sum up my P sub I get 1. Then I can define a valid probability function for any event E. Then let's say for some event E in my sample space, the probability of E is just going to be the sum of the corresponding P sub I, where I ranges over all of those I such that S sub I is in my event E. So that's a bit strange of a notation, but it's quite simple. All it says is that I'm going to sum up the P sub I corresponding to the S sub I in my event. So if my event is S1, S5, my probability is P1 plus P 5. If my event is S2, S7, S11, I'm going to sum up P2, P2 corresponding to S2 plus P7 corresponding to S7 plus P11 corresponding to S11. And that's how you're just going to kind of sum up the corresponding P sub I to the S sub I, right? So sum up the P sub I correspond to the S sub I in my event. So in this case, this is my event E, or maybe in this case, this is my event E. So I probably have to actually close this statement of this theorem correctly. So what did I say? I have a sample space. I find a sample space S1 to S sub n. I'm going to choose some corresponding, basically, probabilities of each of these individual outcomes. Probabilities better be positive, the better sum to 1. And I'm going to assign probabilities of to any event by just summing up the corresponding P sub I corresponding to the outcomes in that event. If I do this, this function, this is a function we defined, takes in an event and spits out some number, then P is a valid probability function. So that's the statement of the theorem. And now we can prove it. We have the tools to do this. What must this satisfy to be a valid probability function? Well, it better satisfy the Kolmogorov axioms. So the proof of this thing is just check that this P, this probability, or this reputed probability function, satisfies the Kolmogorov axioms. So, let's check. First axiom, probability of E bigger than or equal to 0 for any event E that's a subset of my sample space. Or if I define my probability function as I have done here, is this always non-negative? Well, it's kind of complicated, so P of E is the sum of some stuff of some P sub I. I don't actually care what it's the sum of. It's the sum of something. Each of these P sub I is bigger than or equal to 0, and so the sum of whatever of them is always bigger than or equal to 0. So we're good. So check. The first Kolmogorov axiom is satisfied because, as defined, this probability function is always positive. 2. So you can see when I went and defined my probability function here, I had this first condition that all these P sub I, basically the probability of the individual outcomes, is positive. I needed that condition, so I satisfied my first Kolmogorov axiom. And notably, the second condition might be useful for our second Kolmogorov axiom. So the second Kolmogorov axiom says that the probability of my whole sample space is 1. So I actually have to check that. So I'm going to put it in the box, the things I have to check. So probability of S, according to our definition of the probability function, it's the sum over I, where S sub I is in my event. And so my event is S, and I sum the corresponding P sub I. Now, what is this index set? I'm going to argue that this is actually the same thing as summing from 1 to n of P sub I. Why? Which I have S sub I that are in S. Every I has a corresponding outcome in my sample space. That might not be true for an arbitrary event, but it's true if the event is the whole sample space. And so this is actually just maybe some permutation of the sum I goes 1 to n of the P sub I. And I required in my definition that sums to 1. Kolmogorov's second axiom is true. Right? So my second part here, I required that the sum of these P sub I, say I goes 1 to n, is 1. Well, why did I require that? Because Kolmogorov axioms need to be satisfied, and if I require that, then it is satisfied. So the first two axioms are generally pretty straightforward to check. the third axiom here is the axiom of countable additivity. Okay. And this is always kind of the harder one to check. So the third axiom says that if E is some event, so a subset of our sample space, and we have some partition, E sub I, partition E, right? So again, what that means is that E sub I, these E sub I are disjoint, and that the union over whatever the set is, partition E sub I is E, that means they partition E, then third axiom of countable additivity says that the probability of E is, of course, the probability of the union of these E sub I. That's required they partition. And it says I can distribute. I'm going to be vague with my index set. I can distribute that probability over the union and change the union to a sum. So, okay, so this is the statement. It's a bit longer for the third axiom. It says that if I can partition E into some E sub I, then the probability of E is just the sum of the probability of its individual constituents of its partition. So in order to check homomorphism axiom, I need to show that for any possible event E and any possible partition E sub I of E. So it seems like a tall order, and it's a little bit more involved, but it's actually doable in this case relatively straightforwardly. So let's look at how to prove this. So we have our event E, we have a partition. It's potentially an infinite partition. Let's say it's a countably infinite partition. If it's finite, we could make it countably infinite by just tacking on a bunch of empty sets. And that would be a countably infinite number of empty sets. It doesn't make it change the union, it doesn't change the disjointedness. So let's, without loss of generality, assume that my partition E sub I is countably infinite. If it's not, we'll tack on a countably infinite number of empty sets, and then it is. Then recall that E is going to be, because the E sub I partition E is the union, the infinite union of these E sub I. So if I have some, let's say S sub j here, some element of my sample space. I have to use j so it's different than this I here. They don't have to be the same, right? This is some element of my sample space. And if this element S sub j is in my event, then this element S sub j is in this countable union. Right? Simple. If it's in the event, it's in the countable union, because the countable union is the event. Okay. Let's scrutinize this statement here. What does it mean to be an element of a countable union, of an infinite union? It means that it is in at least one. So this means that S sub j is in at least one E sub I, right? That's definitionally, the countable union is this collection of all things that are in at least one of the E sub I. Can it be in more than one E sub I? Pause and think. So it cannot be in more than one e sub I. So we can actually say not at least one, but we can actually more strongly say it's in exactly one of the e sub I. Why? The e sub I partition e. The e sub I are disjoint. So if S sub j is in one of the e sub I, it can't be in one of the other ones. If that were true, they wouldn't be disjoint. So if it's in at least one, it's also in at most one because they're disjoint. So it has to be in exactly one. So if S sub j is an element of the union, it is in exactly one of these e sub I. Okay. So let's put that fact in our back pocket there for a moment. This is just a fact to remember. Let's now look at what we want to show. We want to show is that the probability of E, which we can rewrite as the probability of the union of these E sub I, is the sum of the probability of E sub I. Now, we can expand this left here. The probability of the union of these E sub I, according to our definition of P, so we go back all the way up to our definition of P, we do this sum thing, right? So the probability that we're in the union of the E sub I is the sum over, let's say, j, where S sub j is in the union I goes 1 to infinity, E sub I is the sum of the P sub I. All right, and that comes from our definition we had above, which was that the probability of some event E is the sum over I, such that, say, S sub I is in my event. We sum up the corresponding P sub I. So if we apply that definition, but now we swap out E for this union, that's all we're doing. We're swapping out E here for the union there, right? So, okay. So we want to prove this statement. So we're going to kind of circuitously kind of come back around here. Probability of the union of E sub I is a sum over, whoops, this should be the P sub j. Someone should call me out on that remotely. Sum of these P sub j, where j ranges over the, this should also be a j, over any element of the sample space, say S sub j, that is in this union. Now, let's use our fact. If S sub j is in this union, it is in exactly one of these E sub I. So this is going to allow us to say, and I'm going to write this out and then we'll do some examples, that this is the sum, j goes 1 to infinity, the sum do we want to use j here? Oh, let's use I, just so we don't have conflicting indices. Sum I goes 1 to infinity of the j, such that S sub j is in E sub j, and we sum up the corresponding P sub j. Okay, what the hell did I just write there? Let's think about it, okay? If I have an example here, my example here is that, well, what do I want my example to be? My example should be that, example of this sum. If I write out this whole sum, maybe it's P1 plus, so I'm going to take this here, P1 plus P3 plus P5 plus P6 plus P7 plus P11. I don't know. It's ultimately when you expand out the sum in this step, it's the sum of some piece of i's. And if we look at each of these piece of i's, there's some corresponding, right? They correspond each to, say, this corresponds to S1, this corresponds to S2, or S3, this one corresponds to S5, this one corresponds to S6, S7, S11, right? And we can basically group these. So it's the sum over some j corresponding to some s sub j. So it's some j, in this case j is 1, 3, 5, 6, 7, 11, corresponding to some s sub j, s1, s3, s5, 6, 7, 11, right? And we can regroup these because we know each of these, as we said up here, each of these s sub j is in exactly one of the e sub I. So we can kind of group these. Maybe this one and this one correspond to e sub 1, and maybe this one and this one correspond to e sub 2, and maybe these two correspond to e sub 3, etc. Right? We can basically regroup these from this indexing scheme here to an indexing scheme where we sum over, or where we kind of group them by what e sub j they're part of. So that's what I'm doing here. This first, if I fix I, whoops, back up here, this should be e sub I can sum over all of the j corresponding to s sub j and e sub I. So this would be like e sub 1. And I can do that now for 2. I can sum up, so that would be p1, p3, e2, I could, or p1, p1, p5, p3, p6 are part of e2, p7, p11 are part of e3. And so I could rearrange my sum where it's basically this, the probability of e1, which is p1 plus p5, plus the probability of e2, which is p3 plus p6, plus the probability of e3, so let's say a plus there, which is p7 plus p11. So basically I've just re-indexed my sum. And each of these things in here is the probability of e sub I. If I go back to my definition, that is the probability of e sub I. So what I get here is that this is the probability, the sum of the probability of e sub I, which of course is what I wanted to show at the start. So I've shown this. This is what I was trying to show, which I have now shown down here, right? So probability B is probability of the union of e sub I. You can write out what that means, but I can kind of break that individual sum into the sum of 2, and I recognize each of the terms here as the probability of e sub I, and so this becomes the infinite sum of the probability of the e sub I, and that proves the statement. If we go back up, this is the axiom, and it proves exactly. Probability B is the sum of the probability of e sub I. That takes a little bit of thinking to think through those steps. So I'd stop and I'd think through exactly what's going on here. There's kind of two major jumps. One is jumping here to here. So I have to expand out the probability of the union to e sub I into this step here. I have to make this jump where I basically re-index things. And then I recognize these terms here as I kind of re-recognize these as the probability of e sub I, and I get the sum of the probability of e sub I. So that's kind of our first full proof here. It definitely is worth thinking about for a minute. It's not the most important proof, but it proves what we wanted to show, which is that if we kind of do this simple scheme for a finite sample space, where if I have a finite sample space and I have elements and I can just kind of assign probabilities to each of the elements, to each of the outcomes, as long as each of those probabilities is positive and sums to 1, we can make a reasonable definition, as I've defined here, of a probability measure for a finite sample space, which basically says, oh, just add together the probabilities of the outcomes of whatever event I'm looking at. Okay, I'm going to stop there so we can just run through real quick. So we We go way back up to the start. Today, we defined a sample space. We defined an outcome, which is an element of sample space, an event, which is a subset of the sample space. We gave some examples, and then we talked about axiomatic probability. And so today we talked about what a probability function is. And the probability function, this is probably the most useful part here, is it's going to take an event E, that's a subset of our sample space, and it's going to assign to it a probability measure, P of E, that measures how likely that event is to occur. The rules for what makes a valid probability function are the Countable axioms. They codify some of our basic intuitions about probability. One, probability should be non-negative. Probability something happens should be 1. And then there's countable additivity, which is basically kind of a distributive law that says that I can, if I want to add together kind of disjoint probabilities, I can do that. I can break apart an event into disjoint things, calculate the probabilities of disjoint things, and then kind of bring it back together. In the same way, I can break apart an item into 2 individual things, weigh each of them, and bring them back together, and that's the total weight. This is kind of axiomatizing intuitions we have about measuring things. We can break it apart, measure the individual parts, and bring it back together, and that's allowable. It's allowable as long as things are disjoint. And it kind of gives us the distributive law, where I can distribute probability over unions, as long as the events I'm kind of distributing over are disjoint. We gave some more examples here, and then at the end we talked about the finite sample space theorem, basically as just a way of practicing some of our Countable axioms and proving things. And it basically says what we all know: for a finite sample space, I can assign probabilities individually to the outcomes, and if I do it kind of in a reasonable way, nothing bad happens. What I get is a valid probability. So this is valid, and that is what we proved. We checked the Countable axioms. And this last one is a little bit more complicated, but we checked it, and it's valid. Okay, so I'm going to stop there, and next time we're going to get to proving some of the basic results about the probability function.